Okay, welcome to class for April 1st. Today we're going to be talking a little more about energy and how we can use it to problem solve. So reminders. I discovered that Wiley Plus, although it has a thing that says it allows the students to still access the questions after the due date. Apparently, after the due date, it will not accept any answers. Not sure what the point is of letting you see the questions if you can't answer them, but it's an option apparently. So what's going to happen is I'm going to leave the due dates in Wiley Plus as they are, right? So the due dates will stay there, but once the due date passes, I will extend it to the end of the semester. So if you do get, there'll probably be after each assignment, there'll be a window where the due date hasn't been extended yet. That just means I haven't gotten to it. Don't panic. You can shoot me an email and let me know. And that'll give me a good reminder to keep on top of it, but I'm going to try to do those as we go. The next Wiley Plus assignment due date is for chapter 8, which I believe the adaptive practice is due Friday. Okay, there's also perusal reading due for Friday. That'll be on momentum. So today is our last day talking about energy, although it'll come up again. But we'll be moving on to momentum. And then, which is chapter 9 in our normal textbook, the one that's in perusal. And then the third video experiment, it's not up yet, but I'll post it after class. I'd encourage you to keep on top of those. If you start into it and you have questions, come talk to me. We had some people ask questions after class yesterday, and that works. When I say come talk to me, what I mean is either stay on the line immediately after class, or there are office hours Mondays and Thursdays from 11 a.m. to 1 p.m., or you can always email me. Shoot me an email. We can either set up a time to do a Zoom chat, or we can, I can answer by email. But do have a go at those. The lab is such a crucial component of this class, and somehow we're expected to do it without actually having access to a lab. So this is the best we can come up with. I'll also note, just, you guys have already probably realized this, but we're now in this new version, we're spending less time in class, which means the out of class stuff has become bigger, right? It's going to take you more time probably to do the out of class things now than it used to. That's by design. If I can't have an effective in class, I've got to come up with ways to help you learn the material on your own in some sense, which I hate, but that's where we are. Any questions about any of the course stuff?
I want to about the practice. I got 5 out of 10. And I'm wondering, is it like the clicker questions where it's just you completed the questions, you get the credit, or is that my grade?
So the adaptive practice, if I understand it correctly, and this is fairly new to me too, but it should allow you, it should keep asking you questions until it decides you have mastered the material. And so if you continue doing it, it will, I believe, keep increasing your grade. Again, like I said, I'm new to this, so I don't actually see how it grades me. I just see what it asks me to do.
Huh. Because how it looked on my end was I got 24 questions to answer, and it had me confident I was and submitted, and it would tell me I'm wrong. And then once the 24 questions were done, it was like, you're complete. You can keep doing it eternally, it seems. But what's the threshold for being a complete grade? Yeah, I have no idea.
Yeah, I don't really know how to answer that one either. We'll have to figure that one out. Definitely do complete the one round through. And we'll have to figure out how that factors into grades. But I would definitely say that if you're struggling on those, going through them more than once is probably a good idea.
If I have time, I certainly would like to, but all my classes are taking me about twice as long as they did before. So despite having a huge amount of time to work on schoolwork, I'm still pressed for time.
Yeah, I hear you there. Yeah, we'll have to. I don't really have a good answer to that.
Thank you.
But we'll keep trying. I don't know. This is frustrating for me too. I feel like we are generally asking you guys to do moderately impossible things. So anyway, okay. Well, yeah. Other than good luck. Here's generally my thought on that. Don't kill yourself on these things. If the adaptive practice is, and I can actually go in and look at how long people are spending on that, and after the first one is due on Friday, I'll go in and look at that. If people are spending hours and hours on it and getting whatever 2 out of 10 or whatever magical number it invents, then we'll have to sort of reassess how that works. Okay, any other questions?
Thank you.
Okay, let's get to actual physics as best we can. I did want to apologize. Probably doesn't affect most of you if you were watching this thing live, but I keep messing up the recordings, I keep recording them in gallery view instead of speaker view, which makes when I'm working on the paper, makes it a postage stamp size thing. Yeah, I'll try to do better. Okay, so here's the polling question to start off today. So we've got Marcus. Marcus has a mass of 80 kilograms. He jumps off of a 5-meter tall diving board. How fast is he moving when he hits the water?
Dr. Nelson, when it says 5 meters, is that like the height that he's off
Yes.
from the level of the water?
Yeah. So yeah, assume he's 5 meters above the surface of the water.
Okay, thank you.
Okay, I'll give you another 30 seconds here. All right. Going once, going twice. Okay, let me go ahead and end this thing. And let's talk about this. So, well, let's see here. I want to stop that. And I want to switch over here. Okay. So, what we're saying here, this is a problem we can actually do with kinematics. So I'm going to show you how we would do this with kinematics and how we would do this with energy, right? And hopefully you'll see that energy is a lot easier. So with kinematics, right, in both of these cases, what we're saying here is that there's a person, right? Here's the water, and this distance is 5 meters, right? And we also know the mass of the person is 80 kilograms. Okay, so with kinematics, what we'd say is as soon as the guy leaves the edge of the diving board, he's in free fall, right? So his acceleration is just negative g, which means his velocity is just negative gt, which means plus an initial velocity, but we're going to assume he just, stepped off the edge. And that means his height as a function of time is going to look like negative 1/2 g t squared plus his initial height, right? H. So if we want to do this with kinematics, what we would do is we would use this equation to solve for t. We'd plug it into that equation to get velocity. So at the time he hits the water, his height is 0. So 0 is what happens when you're at y of t water, right? If I plug that in to this equation, I get negative 1/2 g t water squared plus height, okay? And if I move this to the other side, I get 1/2 g t water squared equals height, which means if I solve for t water, I'm going to get that t water is the square root of 2h over g. Then I'm going to take this time and I'm going to plug it back up here to my velocity equation. So my velocity when he hits the water is just negative g times that t water, which is the square root of 2h over g, right? And if I work through, simplify the multiplication, that means the velocity when the diver hits the water is just negative square root of 2gh. Okay, because I can bring that g inside of the square root. It'll cancel, it'll be g squared in the numerator. It'll cancel one of the g's in the denominator, and I'll just end up with 2gh, square root of 2gh. And if I plug in my numbers, because the height is 5 meters and g is pretty close to 10, I've got 2 times 10 times 5, which is 10 times 10, Square root of 10 times 10 means that his velocity when he hits the water will be negative 10 meters per second. So the right answer is D. Okay, that's how I do it with kinematics. Now let's do it with energy. So it's the same problem, right? Same deal. Guy on a diving board, water down here, right? Still got an H of 5 meters and a mass of 80 kilograms, okay? Which, by the way, we should realize early on that this mass isn't going to matter, right? Because if we're in free fall, everything does free fall in exactly the same way. If we neglect air resistance, right? Which we always do in this class, unless I tell you not to. So in this case, the mass doesn't matter. And it won't matter for energy either. So for energy, we need to pick two spots. We need to pick an initial spot, which I'm going to choose up here, and a final spot, which I'm going to choose at the water. So initially, he's got no kinetic energy, and he's got gravitational potential energy of mgh. Final is when he hits the water, he's got kinetic energy of 1/2 mv squared, and his gravitational potential energy is now 0. So I've picked a 0 for my gravitational potential energy to be the surface of the water. Okay, so now all I have to do is equate these two, because the initial energy, I'll add it up, has to equal the final energy, I'll add it up. So I get mgh equals 1/2 mv squared. My masses cancel. I move the 2 over, and I get that my velocity is the square root of 2gh. Okay? So whereas before I had to go through a page of algebra, really this one, once I got it all set up, it was 2 lines, right? I had to write the equation, realize mass cancels, solve for V, done. This is the power of working with energy as opposed to going back to kinematics for this particular problem, because we don't care how long it takes Marcos to hit the water. In this case, we only care how fast he's going when he gets there, right? Now, if we wanted to ask how long did it take to hit the water, kinematics would be the way to go. But that's not the question. The question was how fast, so energy was a better choice. Now, what if you're not sure which is the better choice? Well, generally speaking, if you're not sure, I would try energy first. If you get stuck, go back to kinematics. But energy is usually a lot easier. All right, so if we come back over here and share this thing again. All right, so here's your next question. And for this one, we're going to do A is true and B is false. So you've got a block with mass m with initial speed v, and it slides up a frictionless ramp at a height h, inclined at an angle theta as shown. Assume no friction. Okay, so what the statement I want you to evaluate is whether the block makes it to the top of the ramp depends on the mass of the block and on the angle theta. So let me relaunch the poll. I'll give you guys a minute to think about it. Okay, I'll give you another 30 seconds. All right, going once. Going twice. Sold. All right, this one's interesting. Let me share the results here. So it was almost 50-50. It was 7-5. 7 votes for B for false, 5 votes for A. So let's start with A. Somebody want to give me an argument why the mass of the block and or the angle theta would be what determine whether or not you make it to the top of the ramp?
So the mass doesn't matter because gravity will accelerate it at the same rate no matter what, but the angle can affect it. And so if the angle is too steep for the velocity, then it won't make it up.
So you're arguing that it's the angle that matters, not the block, not the mass.
Yeah.
Okay. So somebody who answered B, what do you think?
If it doesn't have any velocity, it's not going to make it to the top of the ramp, no matter what its mass or the angle is.
Okay. So it would have to have some velocity, right? So, it says that it's got some initial speed, right? So if that initial speed is too small, it won't make it to the top of the ramp. If that initial speed is too big, it will make it to the top of the ramp. But why doesn't the mass of the block or the angle matter?
I don't think the mass matters, but I do think the angle still matters.
Okay. So we've had 2 people so far. They both argue the mass of the block doesn't matter. The angle does. Anybody want to argue that the angle doesn't matter?
I actually thought of an argument for why it doesn't matter.
Okay.
And that's because it's still climbing the same height.
So you're saying as long as the height didn't change. All right, which is actually the correct answer here. The correct answer was B, that's false, because for exactly the reason Lucas said, what matters here, assuming it's a frictionless ramp, okay? That's important. It's got to be a frictionless ramp, because a real ramp with real friction, right, you're going to have issues at the corners. Here, let me, there we go. So in a real ramp, right, these corners matter a lot, because if you have these rough corners, then you bump into things and you get a lot of friction at the corners. But remember, we emphasized here, frictionless ramp, no friction. So this thing is just going to slide perfectly along. So it turns out that what matters here is not how steep the ramp is, it matters how tall the ramp is. Okay? And we can think about this from an energy standpoint, right? If we want it to make it to the top of the ramp, the kinetic energy at the bottom has to be at least equal to or greater than the potential energy at the top, right? And so we can set those two equal to each other. We can say 1/2 mv squared down here equals mgh up here. And then it's the algebra is very similar to what we just did, just in the reverse. Now, here's the cool thing about energy. Energy is not a vector, right? Energy is a scalar, so it doesn't have direction to it. which means that literally this setup we just talked about, the 1/2 mv squared equals mgh, the algebra is exactly the same as what we just did on the last problem with the diver. It's the exact same equation. And the only thing that comes into it, whether or not you have enough velocity to get up here, is gravity and the height of the ramp, not the angle of the ramp. Okay. Okay, this gets into one other component that we talked about of gravitational potential, right? Or conservative forces are path independent. They don't care how you get from here to here. They only care that you got from here to here.
So in this case, we're not really like solving for anything. We're just kind of like conceptual.
Yeah, so I mean, it's the algebra. If you wanted to set it up algebraically, the algebra would look exactly the same as we did on the last problem. But really, what I want you to realize here is that the way you set this problem up using energy, we don't have the angle of the ramp at all. Now, the angle of the ramp will matter, right? A steeper, shorter ramp will behave differently in terms of how long it takes the block to move up here than a longer, shallower ramp. But whether or not it makes it only depends on the height, not the angle. Okay, so now here's a nice sort of video demonstration of this idea. Well, I hope that was a video. Where'd the video? There's the video. Okay, so what we've got here is 4 different tracks. Okay. Okay. Whoop, nope. Go back. Okay, so you have 4 different tracks here that take 4 different paths from the same height to the same height. Okay, and then the balls go off the table. They're all flat at the end here, and then they're going to land some distance away. So I want you to watch the video here, and it'll play it several times, sort of zoomed in, and hopefully you'll get some idea of what we're talking about here. So they release all 4 balls. They all accelerate at different rates, but if you watch them land, they all land at almost exactly the same spot. Let me play that video one more time. Okay, so they all go ramping off. They all experience very different accelerations because they're different tracks. But they all land right in front of that line of tape. So here's the question about this. The fact that the balls landed at the same distance from the end of the ramp means that they all, A, traveled the same distance along the ramps, B, had the same kinetic energy when they left the ramps, C, had the same kinetic energy as they moved along the ramps, or D, experienced the same normal forces as they moved along the ramps. Okay, let me relaunch the poll here, and I'll give you a minute to think this through.
Dr. Nelson,
Mm-hmm.
do you know how I get the poll back? I minimized it because it was blocking the question, but I don't know where it minimized to.
The bottom of the screen, there should be like if you mouse over it, you can see all these options. There should be a polls option.
Oh yeah.
It's to the right
Perfect.
of
Thank you.
No problem.
it's interesting. We're all getting to be sort of, you know, good at Zoom, slowly but surely. All right, I'll give you another 20 seconds. All right, going once, going twice. Sold. All right, most people said B. Most people are right. So the answer here is that they had the same kinetic energy when they left the ramps. Okay, so let's think about these four options, right? Traveled the same distance, had the same kinetic energy when they left the ramps, had the same kinetic energy as they moved along the ramps, and experienced the same normal forces as they moved along the ramps. And let's talk through these, right, as we watch the thing happen again. So right away, all right, I want the zoom in view here. Okay, right there. You can already see that they experienced very different accelerations, right? Because already two of them are completely out of the screen and two of them are right there. Let me go back just a smidge. Come on. I just want to go back like 2 frames. There we go. Okay, so if we do this, right? Oh, no, dang it. Okay, can't. I just want to go like 1. There we go. So you can see that they've already started moving at different speeds, right? If this is a race, the yellow one is winning initially, right? The green and red ones are losing. So they already have different kinetic energies, okay? Okay, if we keep watching, oh, dang it. Man, I am bad at this. Okay. So we watch them go. They all land about the same spot. We watch them go. They all land about the same spot. Okay. I wanted to show. Okay. Well, dang it. There we go. Okay. So here you go. If you look at this frame that I've frozen it on, right? The ball from the blue track is right here. It's kind of blurry even, but it's right there. The ball on the yellow track is right there. The ball on the green track is right there. Red track is right there. Okay. So they've obviously have very different kinetic energies at this point. You can also say that they have very different normal forces, right? Because this yellow ball, it's basically a flat track, right? The same slope the whole way. Okay. This guy is normal force, the red one, normal force is almost straight up, right? The yellow one's normal force is perpendicular. Here, the blue one's is straight up, but when the blue was back up here, his normal force was very different, okay? So what you've got here are very different normal forces. So we've already knocked out the kinetic energies are the same as they move along, the normal forces are the same as they move along. The last one we should think about here is the idea that the, no, I've forgotten it. Come on. Oh, they traveled the same distance. Let me come back and start this thing up again. Okay, you can see here, these ramps aren't going to be the same distance. Okay, what's the shortest distance between 2 points?
A straight line.
A straight line. How do you know that?
Because it doesn't have any bends or curves or none of that.
Because it makes sense, right?
It makes sense. Yep.
It makes sense. It turns out solving that actually takes variational calculus, which if you come take my upper division mechanics class, we will do. We will actually mathematically prove that the shortest distance between 2 points is a straight line. Just as a little aside, that's not true if you're not moving along a flat surface. So for example, the shortest distance you fly, for a flight going from, say, Los Angeles to London is not a straight line. The straight line option isn't even available, right? It's going through the middle of the earth. The shortest distance going along the surface of the earth actually ends up taking you up north, like over Greenland. Anyway, that's not what we're talking about today, but it's an interesting point. So if the shortest distance between 2 points is a straight line, which is correct, right, then this yellow one is actually traveling a very different distance than these other ones, right? They're all taking longer or shorter distances. And interestingly enough, the blue one gets there faster, right? The blue one is the fastest of the 4 balls, faster than the one that goes in a straight line, which actually gets to another problem that we do in my upper division mechanics class. We won't worry about it here. So we can knock out all three of the other options, which means the kinetic energy is the same at the end of the ramp for all 4, must be the one left. But let's talk about that. How do I know that's the case? Well, let me come over here, stop sharing, there we go. Okay, so as soon as the balls leave the ramp, right? Here's my table, and here's where the balls are going to land, right? And all 4 of the balls did this kind of a thing, right? This should be sounding off some alarm bells in your head because this is projectile motion, right? And if they all came off horizontally, then the only thing that would change how far they land is how fast they were going, right? So if they all land at the same spot over here, that means they all had to have the same velocity when they left. And if their velocities are the same and they're the same metal balls, which they are, then their kinetic energies were all the same when they came off the ramp. Okay? So this illustrates sort of in a very graphical way this concept of path independence, right? With energy, as long as we're talking about conservative forces, so not friction, not, tension forces, not normal forces doing work, but just gravity is the only thing doing work here. As long as that's true, as long as gravity is the only force doing work on these balls, it doesn't matter what path they take to go from where they started to the end of the ramp. Their velocity at the bottom of the ramp will be the same. Okay? So there really is this path independence, right? As long as we're only talking about conservative forces, it doesn't matter how they get there, which is kind of fun. Okay? They can do all kinds of crazy shapes and doody-dods, but as long as they get here, they all start at the same spot and they all end at the same spot. As long as there were no non-conservative forces, they will have the same kinetic energy and hence the same velocity, as long as they have the same mass. Which is kind of crazy, right? It kind of goes against experience. And the reason it goes against experience is because it is really hard in macroscopic systems to get rid of friction, right? Because friction is a non-conservative force, which means it does care about the path you take, right? So for real life objects, getting rid of friction is usually very hard. For microscopic objects, it turns out that there is generally no friction. So when we talk about how, electrons move, or how, how subatomic particles work, or how atoms move, or how different atoms in a chemical reaction or mixing problem work. Yeah, there really is no friction, which is kind of cool. Okay, so let's come back up here. Oh, I got to share my screen again. Let's come back up here. Let's talk about roller coasters for a minute. So last time we worked out this the problem with Homer Simpson going around the spherical cage in a motorcycle, right? Basically, that's the same thing as a roller coaster coasting around a loop. Okay. So if we have a roller coaster and it's going to coast around a loop, and for simplicity, let's make our loop a circle, right? We already worked through last time how how to set that up as an energy problem, right? That we could figure out at any point, at any angle along the loop, right? From 0 degree or 0 radians at the bottom to 2 pi all the way again at the bottom, how fast the roller coaster would be moving, or Homer Simpson would be moving, right? Same deal. Okay, so now what we're going to do is we're going to use energy to get forces. Now, this should seem a little backwards to you, right? In the past, we've used forces to figure out energies. Now we're going to do the reverse. We're going to figure out where the normal force on the riders is at the top and bottom of the loop, okay? Assuming they're coasting, right? Coasting is code for no friction. Okay, so let me come back over here to the paper. And this is what we've got, right? This is what we worked out last time. That the velocity that we would get going around the loop, right, was this function, okay? Where V naught was our velocity at the bottom of the loop, right? And this was our this was our contribution from the energy that got converted to potential energy as you went around the loop, right? So remember, we had our setup where we're moving in a circular loop. We have V naught velocity at the bottom of the loop, and then we wanted to figure out what our velocity was going around the thing, right? So let's do the same problem, but now I want to figure out what the normal force is, right? If I go back over here and I ask for a free body diagram at the bottom of the loop, right? There's only 2 forces acting on me. There's gravity going down, right? But there's got to be a normal force going up, because that normal force has to produce a net force that's pointed towards the center of my loop. And I know that because I'm moving in a circle. And anytime I'm moving in a circle, I have to have a net force that is pointed towards the center of the circle so that I can get that centripetal acceleration. So if you remember, centripetal acceleration is just V squared over R, right? And if I want to know the force that causes that, well, that's just my net force divided by my mass, right? They've all got to be pointed in the same direction. Okay, so the question asked for 2 points to worry about. It asked to worry about the top of the loop and the bottom of the loop. So let's do the bottom of the loop first, okay? Okay, at the bottom of the loop, This is also at the bottom of the loop. Okay, by the way, while we're at it, what does the free body diagram look at the top of the loop? Well, we've still got gravity, because gravity is always doing the same thing. But now my normal force is pointed down, right? If you remember from the bucket, the water in the bucket problem, my normal force was 0 if it just barely went around. Now, if you're designing a roller coaster, you really don't want it to just barely go around, because what if it doesn't make it, right? What if it's a little bit off that day? There's a little bit of friction. You really don't want it to barely make it, because then people get stuck at the top of a roller coaster upside down, and that's going to make people really upset. So you want to make sure you have enough to clearly make it around, and if you make it around with a little extra, you're going to need some normal force to do that, right? Okay, so there's the free body diagrams for the bottom and the top. Let's do the bottom first. Okay, so we can take this equation and bring it down here. So our v squared, well, we know what v is. We've worked that out before. So squaring it just gets rid of the square root. I'm going to end up with something that looks like 2gr times cosine theta minus 1 plus v naught squared all over r is going to be equal to, now I've got to think about what my net force is, right? My net force is my normal force minus my gravitational force when I'm at the bottom, because the normal and the gravitational are going against each other, okay? Now, there's one more thing I can do to make life easy. Cosine theta, right, is I can put in theta. At the bottom, theta is 0, the way we set this up. So cosine theta is 1. 1 minus 1 is 0, which means this whole term drops out. So what I get is something that simply looks like v naught squared over r equals my normal force minus my gravitational force over mass.
Can you move the paper up some?
Oh, yes, I can. Here, let me actually, can you guys see that now?
Barely
A little
at the
more?
bottom.
All right, we'll go a little more up. Come on, paper. There we go. Okay. So our normal force, we don't know. Our gravitational force, we do know. It's just mg, right? So if I break up this fraction, I'm going to get normal force over mass minus mg over mass. My masses cancel, right? And if I get myself a new sheet of paper and move back down, okay, what I get is that my v naught squared over r plus my g, right, 9.8 is going to be equal to my normal force over my mass, which means that my normal force is going to be m v naught squared over r plus mg. In other words, it is exactly what we said it was. It's the piece you need for the centripetal acceleration plus the piece you need to cancel out gravity, okay? Okay, so that's the bottom of the loop. Now let's come back to the top of the loop. And let's look at what happens up there. Okay, we can use the same thing, right? Our v squared is just 2gr times the quantity cosine theta minus 1 all over, or plus v naught squared all over r is equal to our net force over our mass. Okay? Okay, at the top, our theta is pi, right? Pi radians, straight up, 180 degrees. So that means the cosine of pi is -1, which means that now this whole thing in the parentheses becomes -2. -1 minus 1 is -2. So what I get on the top here is something that looks like -4gr plus V naught squared all over R equals, and now I've got to worry about the net force. Remember, both my gravitational force and my normal force are in the same direction. So I end up with normal force plus gravitational force divided by my mass. Okay. Okay, so we can simplify this a little bit, right? With the same way we did last time, we can realize this is normal force over mass plus my gravitational force, right? And I can come down here now and I can clean things up a little bit. I can distribute this R, right? I'm going to end up with minus 4G, because these R's are going to cancel, plus V naught squared over R is equal to my normal force divided by my mass plus G. I move that G over. I get, and I'm going to rewrite this just in the ordering, V naught squared over R minus 5G equals my normal force divided by my mass. And finally, if I solve for my normal force, I get that it's m V naught squared over R minus 5 mg. Okay, let's compare these two, right? This term is the same in both of them, right? Same term. Now, at the bottom, I have to add the weight. At the top, I get to subtract 5 times the weight. Now, that seems crazy, right? Why on earth do I get to subtract 5 times the weight? It's because two things have happened. If we go back to my picture, right? At the top of the loop, my velocity has dropped a lot, right? I've lost a lot of speed because I've gained a lot of gravitational potential energy. Okay? So the reason I get this really dramatic 5 times the weight decrease at the top is because not only is gravity helping me go in a circle here, as opposed to up here where gravity is opposing me going in a circle, but I also lost a bunch of speed, okay? So what this means here is that the bottom of the loop is actually the part that's hardest on the riders, not the top of the loop, okay? I have to be going fast enough that I make it, right? That this number doesn't become negative, because if this number becomes negative, something's broken in my problem. It means my normal force is going the wrong way. Okay. It also means my velocity is going to be less than 0 at some point, which means you're going to start falling back the other way down the ramp, right? But so I have to have enough to make it. But when I get to the top, the normal force is reduced a lot, which is nice for the rider, right? That's why when you go around the top of one of these things, you get that almost weightless feeling. It's not, you're not weightless, but the normal force, right, is almost being canceled out by your weight. Okay? Whereas up here at the bottom, you get really slammed into your seat because the normal force is having to counteract both your weight normally and make you go in a circle. Okay, this gets at an interesting point in how you design loop-de-loops in real roller coasters. So let me come back over here and share this thing. Okay, if you look at this picture, it's a funny shape. It's not a circle. So what have they done to this roller coaster? Why did they make it this weird shape that's not quite a circle?
Build up speed.
Well, kind of. Why didn't they just make a circle the same height? Right? Instead, they made this weird kind of teardrop shape. So what I want you to do, go ahead.
Is it so that you experience less acceleration when it moves, like in different ways? So if it was a circle, you'd experience a lot more when you approach and then end the loop?
Yes. It's because the circle, right? What we just worked out is the circle puts a lot of force on people, a lot of normal force on people when at the top and bottom of the loop, right? At the bottom of the loop. So what they've done here is they've said, okay, we can fix that. They realized that you don't have to have the same radius of the circle all the way through. So if you look at the bottom, the radius of this circle is big, right? If you were to draw a circle that kept going around like that, it would be huge, okay? Up here, the circle is small. So what they've done is they've chosen a shape where the radius of the circle, the radius of what you're turning around, decreases as you go up. So let's look back over here at our formula, okay? If I put in a big radius here at the, at the bottom, I put a big radius in here, that's going to lead to less normal force. Less force on the people going around the circle, right? If I put in a small radius down here, that's going to lead to more normal force on the people, okay? So what this teardrop shape is basically it's optimized so it gives you not exactly, but close to constant normal force on people going around the loop. By changing the radius of curvature of the loop, right? So you have a big radius of curvature at the bottom. That makes this term small. You have a small radius of curvature at the top. That makes this term big, right? And then it gets a bunch of stuff subtracted off of it. You can make it so that you don't smash people into their seats at the bottom of the roller coaster, and they still get that fun feeling of, flipping around the thing up at the top. Okay? So it turns out that almost all Ferris wheel roller coasters look like this. It's very rare to find one that's actually circular. They're almost all this kind of funky teardrop shape for exactly this reason. Okay, questions? Okay, so to review, if we want to solve these problems, right, these energy problems, what we're going to have to do is we're going to have to be able to identify what energy we have to worry about at each point, right? Do we care about kinetic energy, potential energy, gravitational potential, spring potential energy? The nice thing is in this course, those are the only three energies we're going to worry about, okay? Kinetic energy, gravitational potential, spring potential. We're going to have to ask, are there any non-conservative forces? Now, on a real roller coaster, there are non-conservative forces. As much as you try to make it frictionless, there is friction on the roller coaster. And as much as you try to reduce it, you do have drag, air resistance, right? So those will mean you lose a little bit of energy. But when we do energy problems, if we want to talk about conservation of energy, we can only talk about three different things: kinetic energy, gravitational potential energy, spring potential energy. We can combine them, we can mix and match, right? I can invent all kinds of interesting problems that do one and not the other or both, right? But I only have 3 choices. Now, that's not true. There are other types of potential energies. When you get to electromagnetism, 204B, you'll learn about electromagnetic potential energy. And, you'll learn about energies, chemical energies, when you take chemistry, or when you talk about 204C, you talk about thermodynamics, you'll learn about thermal energy. There's all kinds of energies running around out there. But for this class, we only have to worry about 3. Okay, how are we feeling?
All right.
We'll take an all right. That's about as good as we can hope for. Okay, so what I want you to be sure to do, the homework, the Wiley Plus, for this, that is for chapter 8. Okay, now this is where it gets a little confusing. The books use almost the same chapter numbers, right? They're structured in almost the same way. So the Wiley Plus chapter 8 is technically referring to a chapter 8 in a different textbook, but it's also on potential energy and conservation of energy. Okay, and chapter 9, which is where we're going on Friday, talks about momentum, is also chapter 9 in the Wiley Plus book. We'll lose that a little bit when we get to rotation. They don't match up quite as well there, but for now, they match up really nicely. So have a look at those problems. Different people learn effectively in different ways, but I have yet to meet a student that can really master the material in this course without slogging through the homework. And I wish you could do it in 110. I really wish you could do it in the tutorial lab. I wish you could come to my office hours. Unfortunately, this is the best we got. So I'm more than happy to stick around after class. And if you have questions on homework, fire away. As I mentioned earlier, I'm going to keep the due dates up until we hit them, and then I will push them back. So there may be a short period where it says that the due date's passed and you can't submit. Don't worry about that. It'll come available again in a little bit. And yeah, we'll get a better idea of sort of where people are and how things are going. Okay, I've said it before, but it's hard for me to teach this class, not because of all the logistic things. I mean, those are hard too, but it's hard for me to teach this class because I feel like I'm asking you to do a much more difficult thing than I was asking you to do at the beginning of the class, right? This is hard stuff to learn, and it's going to be hard stuff to learn no matter what format. But some formats are better than others, and at least as far as physics is concerned, online sucks. It really does. So we'll do the best we can. We will survive this thing. We'll learn the material. We'll get through. And if you have, things I can do to help, please let me know. And yeah, we'll make it through. All right. With that, I'm going to stop the recording, and I'll stick around for questions.